Alrighty, and we're back. We are going to take a look at some torque problems now. This problem here is a pretty popular problem on the interwebs. It comes from Mastering Physics, and it deals with a ladder at equilibrium. As you can obviously see, I am a terrible artist. So we have here a ladder. This white beam is a ladder. We got a person up distance d from that ladder. This is going to be the midway point of our ladder, L divided by 2. This whole thing is L, by the way. Then we have two N1, N2 forces, force normals, and then static friction. I've included a link to a much prettier looking diagram in the comment section header, whatever. So if you want to look at something that is a little more clear, please look at that. Come back here, and this should make a little more sense. I tried putting in some butterflies to maybe make up for it. But anyway, let's get started here. So what they're asking for is the minimum coefficient of static friction. That's going to be this force right here that is going to take to keep this ladder from sliding away and this poor man from falling. So let's do some basic, we know it's at equilibrium, so we can do some things right away. One thing we can do is we can say, okay, well, we know N2 is going to be equal to the forces in the up direction have to be equal to the forces in the down direction. So we know that it's going to be equal to M1 G plus M2 G. The person is going to be M2, and the person is M1, and the ladder itself is M2. So we know that these two forces have to equal the force going up. They have to balance each other, right? Otherwise, we're going to be, either accelerating upwards or flying through into the ground. Either way, not good. So we know that. Now, we also know that N1 has to equal the force of static friction, right? Now, we can also do something else. We can say, well, I know that the force of static friction actually is equal to N2 times the coefficient of static friction, right? Well, boom, that's easy. Well, that's going to come in super duper handy later in this problem, so remember that. It's very likely I'm going to erase that halfway through because I don't have a lot of room and there is a lot of work we have to do for this problem. So if you're going along on your own note piece of paper, write this down. This is very handy. So next we need to find the lever arm because we know we need to find the torque, right? Torque is going to be our main thing here because one thing we know for sure, that is not a very good, I think that's what torque looks like. We know that the sum of torque is going to be equal to 0 because otherwise this ladder would be either, like flowing this way or flowing this way, but it's not. It's not doing either of those things. It's at equilibrium, so torque has to be 0 as well. So we need to find the lever arms because the formula for torque equals the lever arm times the force being applied. That's important too. Must know that. That is a very big part of rotational physics, especially when we get into later forces and stuff in chapters. So how do we find the lever arm? Well, a lot of you are thinking, oh, well, that's easy, Joe. This is just going to be D, and this is just going to be L, and boom, those are two lever arms. Well, you are absolutely incorrect. That is not how we find the lever arms, and this is a tricky thing about this ladder problem, is the lever arm is defined as the perpendicular distance from axis to the action line. Now, what does this mean? That's kind of confusing part of mumble jumble there. So let's do a little example here. Let's say we have let's just draw another ladder. I'm going to change colors up here a bit now that we're down at the bottom of the screen. So we have our ladder, and it's going there, and we want to find out, let's just say we have a force being applied here, and it's going straight down. So in order to find the lever arm, we need to find the perpendicular distance from the axis. Now, I can't just draw that there. That's not perpendicular. I'm going to go ahead and undo that because that was pretty bad. So what I need to do is okay, well, I'm going to do a dotted line, down, 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 down. Oh, well, look. Now that I have this is my action line right here, I'm going to put a little right angle. Well, now it's the perpendicular distance. So I know, okay, between the action line and the perpendicular angle of my force, so now I can tell you that this line right here, that's our lever arm. That's what we want to find. Now, we also know, at least from our ladder, that this is theta. So how would we find that? Okay, blah, blah, blah. You do your trig, sub, whatever. Eventually, it's going to ending up being cosine of whatever this force is. So now, for example, so our first one, we know that this is going to be d. Let's just pretend, like let's move this whole thing up and make it fit into this little triangle here. We know that this distance is going to be d, which means that this would be d cosine theta. So that is one. That's our lever arm for this little guy here. Now, let's just take this to the next one. You could play along with home. We are going to do the bigger one. So let's say now we're going the midway point. So now, instead of d, the distance is L divided by 2. Well, we have our force here, and this force goes down here, but I need to find it that it intersects perpendicularly with the action line. So I'm going to keep going down, keep going down. Oh, perpendicular, boom. So now I know that all of this is going to be my action line. So I know that the second action line is going to be L divided by 2 cosine theta. Now, we need to find the other one, which means we need to find out this lever arm, because we found for both of these, so we can find the torque for both of these. Because remember, there's going to be a torque going in one direction and the opposite direction, so plus and minus, and they're going to cancel each other out. So, excuse me. So we're going to need to now figure out the torque for the lever arm. I'm sorry, for this force here. Now, some of you are saying, oh well, it seems like we just got a pattern here of we're just going to put cosine. Wrong, incorrect. Do not do that. That would be very bad. I'm going to go ahead and erase this since it seems we're getting the point here. Let's just redraw it. Lost my marker here. Okay. So we're going to redraw that little arm here. Now we have N1. Now if this is theta, this is a perpendicular angle, which means this is theta minus 90, which means going off of trig, this is also equal to theta. But now it needs to be perpendicular to the action line, because remember, these are my two action lines of the actual hinge. The whole thing is hinged right here. So I keep going, I keep going, I keep going, I keep going, boom, perpendicular. So now, this line right here, this is going to be my lever arm. Now, can I use cosine for that? No, because cosine is going to give me this line. I don't want that line. I need this line. We're going to have to use sine. So we know that our third and final lever arm is going to be L, because this is the length of the entire ladder, L sine theta. So now, let's go ahead. I'm going to erase a lot of stuff here, so if you need to copy anything down, please pause the video. Erase, 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 erase. We'll leave that for now. So let's just do a quick put all our torque. We're going to make a real fancy torque summary here. We know that the sum of all torques is going to be equal to. Now remember, torque is the lever arm time multiplied by the force. So let's do the person first. So we know the person was m1. So m1g, that's the force, by d cosine theta. Okay, that's one. Plus, what was the second one? Well, the ladder was going to be m2. So m2g. Now, what was the second with the ladder? It was L divided by 2 cosine theta. And now this is all. And remember, the torque going in this direction has to equal the torque going in that direction. So I'm going to put a minus here, and it's going to be N1 L sine theta. This is a key formula. So if you're writing stuff down, you're writing this down because this is a big deal. So we have found out what the sum of torque is, and we know that this is going to be equal to. Another way we could write this is saying put an equal sign here. Since it's minus, it's just simple addition of plugging it in the other side. We'll go ahead and write this. Again, about to erase a lot of stuff. Write down anything if you need it. So now, remember this formula actually that I just erased. Sorry about that. But I would make another video, but we're already 9 minutes in. So N1. Now remember, N1 I found I could plug into, and I said N1 is equal to the coefficient of static friction, N2. This is equal to N1. Oh, okay. Well, because now remember, I'm trying to solve for this. Well, I can't solve for this. It's not even in our general formula here. But now I can go ahead and erase this and put in US the coefficient of static friction, N2. Okay, but I also have this N2 in here. That's not good. You know, I need to get rid of that because I'm only supposed to have M and L's. Well, we also had on our formula up here that N2 was equal to M1 plus M2 G. You guys see where I'm going now? So now we plug that in, which is going to be a little bit more difficult. Let's rewrite it up here. Pick a different color since we're going to be getting pretty fancy now. So now I'm gonna rewrite some of this stuff so it's a little more simplified and easier to cancel out. So it might look a little different, but trust me, it's the exact same formula. We're gonna have M1 G D cosine theta. Oh, apologies. Plus M2 G L divided by 2 cosine theta is equal to static friction. Now we got to plug that in. So M1 plus M2 G L sine theta. I think I got that in there. So now, okay, something easy to do first here is let's go ahead and cross out these G's since they're all over the place. We're going to divide everything by G and we can go ahead and get rid of it. Now let's go one step further up. You see what I'm doing here of all we're going to do is we're going to divide all of this by this. And that's going to let us solve for the coefficient of static friction. Now, that final answer is going to look a little something like this. Let's go back to purple here. So the coefficient of static friction is going to be equal to, this is where I'm going to, apologies, really simplify stuff here. So M1D plus M2 L divided by 2, all that in parentheses, and that's going to be multiplied by cosine theta. And then that's all divided by this, which is just M1 plus M2 L sine theta. That is going to be our final answer. That is what the coefficient of static friction must be if we are at equilibrium. So a prime thing that you're going to have to take away from this is how to calculate those lever arms, because that is key. You need to remember that it's not just, oh, well, it's just, the radius. No, it's not. It's the perpendicular. The perpendicular distance from the axis to the line of action. So you need to take this down, find it that, boom. Where it hits that hinged line of action, that's going to be your lever arm. Once you calculate that, the rest of this is just simple equilibrium stuff that we make equal to each other. I know this was a long video. I did try to go quickly. This is kind of a big, long problem. If there's any other questions, go ahead, shoot me something in the comments, and I'll try to clear it up.